Sup, you 11s? How's it going, guys? Right, so today's lesson is on Equilibria Part 3, Lesson 3 of the series, and we're going to be looking at Le Chatelier's principle today. So just, I'm going to crack straight on, don't want to waste any time. So let's share screen. Let's see if, I've got a little fan that now sits at the back of my laptop. Oh, my laptop's struggling already. That's not a good sign. Let's turn that off. Oh, my laptop seems to be taking a break. That was a bad start, wasn't it? Close all windows. Oh no, close all windows. My laptop's crashed before I even turned off the camera. Really? It's because it's pretty warm. This is not going well. Close. Back now. There we go. Sorry, I'm back now. Oh, there's now two of me? What? I have no idea why I would split that. It says that means that there's another one running. Solo layout. Nope. I'm back now. There we go. Sorry, I'm back now. Oh, there's now two of me. What? I have no idea why I would split that. It says no. This is not going well. Solo layout. I can't seem to find the. This is going all kinds of wrong. Okay. Oh my goodness, literally ×2. I know, yeah, we definitely don't want to have that. That would be crazy. Oh, that's interesting. I can't seem to find wrong. Okay, so that's so strange. Oh, it seems to have sorted itself out now. Fine. Okay, back to this then. So let's try sharing my screen again. See if it does that. Oh, seems to work now. Fine. All right. Click on that one. Okay. So at this point, what I'm going to do is I'm going to turn off my. I've got way too many tabs open. I'm going to double trouble. Oh my goodness. I think the chat's already popped out actually. Yes, it is. So now that I know that the sound's working okay, although it's not great quality, I'm just going to close that one down. There we go. Okay, I'm also going to, this is not going to go well, guys. I feel like I really want to try and turn, oh, right. If I click on a different window, there we go. I click on a different window. I want a window where I'm not showing my camera anywhere. Let's see if this crashes. I'm sorry if it crashes. It's not crashed. Yay! I'm on. Okay, guys, we're there. We're there. Always takes a while to get this set up, doesn't it? Okay, so last lesson, we did a quick review in the first 10 minutes of the lesson, looking through the previous notes. Yeah, we talked about the features. We talked about this idea of where positions lie and how it takes time for an equilibrium to be established. Yeah, we talked about good and bad positions, depending on whether it lies to the left or lies to the right. We've talked about yield, and we now get to conditions. So today's lesson is on Le Chatelier's principle. How cool is that, guy? That is one serious mustache. Like, I have massive respect for that guy. He's uber cool. So we've got, okay, 3 learning objectives today. Number 1, know the conditions that affect the equilibrium position. Technically, we've already actually achieved that one from the last lesson. Yeah, it's nice to have you guys contribute on the chat since the chat is available. I'm just trying to minimize all my other screens. There we go. So yeah, camera not, let's get rid of that now. There we go. So the chat's available. So nice reminder. So everyone in the room, just take a minute and I'm just going to write down the conditions, and you guys can pause the video and have a go at doing them as well. So the conditions. Make my pen a bit thicker. I'm not going to write in black and in red. I'm going to write black. So conditions. Well, that's really too thick now. It's really annoying. Not doing a good lesson today. Conditions. Conditions that alter the position of equilibrium, of an equilibrium. An equilibrium. Cool. Okay, so 3 conditions, and those 3 are temperature. And what I'm gonna do is temperature. I'm going to teach these in this order. So the first one I'm going to focus on is temperature. The next one I'm going to do is pressure. And then the third one is concentration. Okay, so each of these 3 things has a very particular explanation. Now, the reason why I give it in this order is because this was the order. This was actually probably wasn't. If I'm honest, I think Le Chatelier himself, I think, did it in this order: concentration, and then he followed it with pressure. Now, Le Chatelier was an amazing man, Henry Louis Le Chatelier. And he was a French chemist. He did all kinds of amazing stuff in his lifetime. He actually was. He worked in the mining industry. He was very wealthy. His family, and due to him being wealthy, his family put him through a very expensive education. He went to university, studied chemistry and mathematics, I believe, and he ended up going to work in the mining industry. And during his time in the mining industry, he created all kinds of really cool devices that were used in order to improve the quality of life of miners. One of them, I believe, was actually a type of heat pump called it wasn't Peltier, but it's a type of heat pump using dissimilar metals, which was really interesting. But for all of the stuff that he created, all of the discoveries he made, the one that really put him on the map was equilibrium chemistry. So now Le Chatelier, because he was a very hands-on chemist, he actually was a master glass artisan. He used to make all of his own equipment. I don't know if I've got pictures of stuff like that. He actually made his own. I've just closed something and I have no idea what I closed. Reopen, close tab. He actually used to make his own equipment, and he used to make things like, yeah, that'll do. He used to make stuff like this. This is one of his famous ones. So he used to make essentially these kinds of like hand-blown volumetric flasks. That's a volumetric flask, by the way, in modern chemistry speak. He actually also created his very own one. So if you actually do Chatelier himself, he actually put in his name. I believe there is a version of this flask which he invented, which is a rather odd-looking device, which you don't really see anymore. Le Chatelier. Oh yeah, he invented this one here, which is rather interesting. It has this rather odd bobble in the middle of it, which is really, really interesting. But this was one of the pieces of equipment he used to make on a regular basis. I don't really understand the function of the bobble. It's because the whole point of the narrow neck is that small increases in volumes lead to a large increase in the height of the fluid in the volumetric flask. You measure very small quantities upon their addition. And I don't really quite understand what the bobble was there for. But this is one of the ones that he used to make. Anyway, so he used to make his own equipment. And along with his own equipment, he used to make these enormous vessels. And he'd actually, so when you entered his house, he'd have these glass vessels everywhere, and these things were big. He'd have huge glass bottles containing all kinds of weird chemistry. And one of the things that he spent a lot of time with was this reaction. So this reaction became a bit of an obsession for Le Chatelier. If you take copper metal, which is pink, if you take pink copper metal, I'll go for that one. You take pink copper metal and you add it to concentrated, and it has to be concentrated nitric acid. What happens is you form copper nitrate. Got to be careful on the number there. That's nitrate 5. Copper nitrate 3, I believe. I've got to be careful on the formula of this guy as well. NO2 twice, I believe. Is that correct? Was it NO? I've gone and got myself lost on an equation. It's a rather odd reaction. This is why I'm not 100% sure on it. It's lovely that I've quoted it in a lesson and not realized. So let's do copper and nitric acid reaction. And I want the equation. It's an odd copper salt. Oh, no, it's not. Oh, okay. So it's not an odd copper salt. It's copper 2 nitrate plus NO2 and plus water. Should be able to balance that at that point. Nope, that doesn't work. So one copper, one hydrogen, 2 hydrogens. All right, let's do it this way. Let's do the long way. Right, 2 hydrogen, 2 hydrogen, 2 nitrogens. 3 nitrogens. So I'm going to need another one there. Yeah, 3 nitrogens. But now my hydrogens are out of sync. Now the common denominator between 3 hydrogens and 2 hydrogens is 6. So what I'm going to now do is I'm going to make that into a 3, and I'm going to double that one, make that into 6. I don't want to do that. I'm going to go back to my normal numbers now that they're getting too large. So that should now, I should now be able to do 1 copper, 6 hydrogens, 6 nitrogens. Right, common denominator. But I've got 6 nitrogens. I don't really want to affect the... Okay. Now, guys, these are kind of equations. This is why equations are hard in chemistry. Trying to balance that purely from a numbers perspective is disgusting. And I'm getting lost with it. Right, what I'm now going to do is I'm going to switch to a method of balancing this equation using half equations. This is balancing it from a redox perspective. So the first thing that's happening is I'm having HNO3 is becoming NO2. So we can balance this half equation. So 1 nitrogen, 3 oxygens, 2 oxygens, common denominator 6. Oh no, hang on a sec. Hang on a sec. No. Sorry, I'm not going very well today. Add water for oxygen. Ooh. Hydrogen, 2 hydrogens, add H plus. Add an electron. Right, so that's what's happening. So this process is gaining electrons. Yeah, there you go. So that's in. Yeah, gain is in terms of electrons. So in terms of oxidation is loss and reduction is gain. That's reduction. That's the red reaction. And it's needing 1 electron to do that. The other equation is copper. Copper is going from copper neutral to copper 2 plus. Copper 2 plus. So what I can now do is I can balance for that one as well. Now it's going to need 2 electrons. Right, so what at this point I can do is I need the top equation to give me 2 of them. So multiply 2 electrons. You need the electrons to balance for reactions to happen. So I'm going to multiply this by 2, 2, 2, and 2, and 2, and 2. Right, and then, so my numbers. So I should be able to now put them together. The problem is there's a neutralization reaction going on as well, I believe. So if I put a 2 here, and I put a 2 there, and I put a 2 in front of the water. But then we need our H pluses. So we need an acid. We're going to need 2 acids to provide that. The H pluses goes in the same form as HNO3. So I'm going to need 4 of those now. And the second equation, I'm going to need 4 H pluses. Nitric acid dissociates to give me 4 H pluses. I need 4 of them. Is it 4? No, 2. I need 2 of them. 2 of those, give me 2 of those, and then 2 NO3 minuses. Right, so the redox equations I can put together. I'm going to need 2, so the nitric acids, these cancel out when they go together. The H pluses now vanish. Now I can put them together. 4 nitric acids, 1 copper on that side, 2 NO2s, 2 waters. Does that now add up? Does that add up? I don't know quite how I got so lost in that. 1 copper, 4 hydrogens, 4 nitrogens, that's good. Oxygens, 12 here, yeah, 4 times 3, and then 6, 10, 12, all adds up. Nightmare. So anyway, it's nice to show you how chemistry does evolve, and that kind of equation's not the nicest one to get. I could have done it much easier, having just spent a bit more time thinking about it and not rushing it. But anyway, so now we've got a balanced equation. Now, the reason why Le Chatelier got so bothered was so bothered by this reaction was because it made a rather interesting product. It made a brown gas. And you need to know this for GCSE. Yeah, so this is a nota bene that you guys have to have for your GCSE exam. So nota bene, NO2 gas is brown. I should have done it in brown, shouldn't I? There we go. Is a brown gas. Okay, so the reason why he kind of got obsessed with this, because the reason why he was obsessed was because, you know, most gases don't have colors. By the way, there's actually a writing in his journal about him doing this reaction, and he talks about how when he adds the copper, it splashes on his pants and the nitric acid dissolves his trousers. He does it in a nice French way, but it's actually very entertaining. You can look it up. It's quite fascinating. I'll see if I can find the link and share it. But anyway, most gases that that were being discovered at the time, most of them were colorless. You know, there are a few exceptions. You know, chlorine having a pale green color, and of course bromine being brown. But bromine was rather nasty and very dangerous, and so Le Chatelier didn't really spend an awful lot of time doing it. He didn't like to mess around with bromine because bromine kills people. Yeah, so he used this reaction to fill rather large glass jars with this brown gas. Now he used to store them. He used to store them in his lab. Now this jar was filled with this brown gas, and every morning he would come into his workplace, into his laboratory, and he would walk past the jars were actually by the door. So when you walked in and you had this rather nice hallway towards his laboratory, there were these wooden shelves with bottles and bottles of different chemicals, and one of them was NO2. And he made a rather unusual observation. So what Le Chatelier noticed, so Le Chatelier made an observation. Le Chatelier observed that the color of the gas, appeared to fade in on cold days. Fade on cold days. Now, when he made this observation, initial observation about NO2 gas, he then started a diary. And what he did was he was recording the temperature of his laboratory and recording the color of the glass jars. He then set up a variety of these bottles, all with different quantities of NO2 gas in it. So in one bottle, he added a large amount of gas. In the other one, he added very little gas. And he That's why. And then turn off mute. I don't know. I don't know what's going on. Guys, I've really messed today up. Can you hear me okay now? Such a disaster. Can you hear me okay, guys? Give me a quick shout out on the chat if you can hear me. You can't hear me, can you? Yes, works now. Okay. You'll just have to cope with my little image over there. Oh, no, you don't have to. I can put it there. Okay, cool. So what he decided to do is he wanted to actually do experiments on the effect of temperature. So the first thing Le Chatelier did was he took out the gas from the jar and he did a variety of reactions to try and figure out what actually was happening in terms of the particles. And he made a rather lovely discovery. He discovered that NO2 gas, NO2 gas actually reacts with itself to form N2O4. This is nitrogen tetroxide. I know, right? These two, by the way, the equation can be simplified, of course, down to that, but I wanted to show you the particles there. There was a very good reason for that. And this side is brown. This side is a brown gas. And this side is a colorless gas. So we started off with nitrogen dioxide as brown. And it formed dinitrogen tetroxide. Dinitrogen tetroxide. I'll put it down at the bottom. Dinitrogen tetroxide. You don't need to know the name of that one, by the way, guys, but it's cool to know it. And it forms a colorless gas. Now, he realized that there were two people in the jar. Now, at this point, he was like, ooh, hang on a sec. So what he realized was if he altered the temperature, then some of the NO2 gas, then the amount of NO2 gas he could see would change. So here's what he now saw. So he took, and by the way, you can find various pictures of his, I think actually there are pictures on the internet of his entire setup. But he essentially, let's see if I can find an image of this. Let's do NO2 temperature. I don't know why it's on that. Yeah, oh, that's not what I want. There you go. So I just want the image, actually. I don't actually want any of the maths. That's part of A2 chemistry when you start looking at it from there we go. So when you have this setup, and I'd love to be able to just take the image, but it's not. That'll do. Oh, come on. That'll do. There we go. If I click on that one. So he wrote down an observation. He said, I'm going to take my jar. I'm going to take my jar of NO2, which I've made through the reaction of copper with concentrated nitric acid, and I'm going to put it into various temperatures. And so he sealed it in a jar, which he probably already had in reality, and he just shoved it in an ice bath. So all he did, he shoved it in an ice bath. And what he noticed was a rather interesting observation, that the color definitely got lighter. That was the main observation. So when cooled, brackets, lower temp, when lower temp, it became lighter. The observation, when cooled, observation was it becomes lighter. It went from a dark brown color to a lighter brown in color. So it would fade. Now, can I just point out, he never managed to make it go colorless the way that you saw in that particular image. He never actually managed to get that. He didn't need to. He wasn't really particularly bothered about how far he could push it. I think he predicted the temperature of it would be required. And at those days, it was quite difficult to get those kind of temperatures. So he didn't bother. But the observation was when he cooled it, it got lighter. Back to black. There we go. It becomes lighter. So what he decided was happening here was that when he was cooling it, the reaction was going in a particular direction. So observation and his explanation would be, he explained it by saying that lower temperature favored the forward reaction. The forward reaction to make N2O4 gas. So he made the observation lower temperatures are favoring it, and this word became super important, favored. Yeah, that's going to become important later. The next thing, of course, is he then, of course, heats it up. And when he heats it up, so at higher temperatures, experiment number 2, yeah, at higher temperatures, at higher temps, the gas darkened. The mixture darkened. Now, this was a rather interesting observation for him to make. And what he needed to do is he needed to try and explain what was going on. Now, if we look at this, oh, my phone is going crazy. I'm so sorry, guys. It's really doing my head in. Oh, we can't hear you. Can you guys not hear me? No, you can. It's all right. It's everybody else. It's doing my head in. I'm just turning my phone onto silent. There we go. So what he needed to do is he needed to explain this observation from a chemistry standpoint. And what he discovered, what he then wrote down, was that what he realized was this. If we look at this from a purely bond perspective, now you've got to be careful with NO2. The bond diagram is rather strange. It's a very odd molecule, NO2. But I'm just going to draw this. Got to be really careful here. NO2 looks like this. Looks like that. And I know it's strange, guys. I don't want you to worry too much about it. Yeah, you don't need to. Now, what he realized was happening was the two molecules were coming together. They were combining together to form a larger molecule. They were forming a bond. So this was the bond they were making. Now, we know from energetics that making a bond, that reaction there is making bonds, otherwise known as mexo. Yeah, mexobendo. Yeah, mexo, making bonds, is exothermic. So this reaction here was producing heat minus delta H. That one is exothermic. That's the symbol. Remember that because we've just finished energetics. It's nice to see how these things now come back together. Yeah, so we realized that it was making a bond, and then that process was exothermic. What he then also realized was that the opposite direction, the counter argument, was this, went from N2O4 and was splitting apart, and it was breaking. Now, what he then knew of this was, in order to break bonds, you have to input energy. This process here is endothermic. Yeah, breaking bonds, bendo. Break bonds, endothermic, bendo. Mexo, bendo. Love that. It's one of my favorite things. I didn't even invent it. Very upsetting. Now, what he realized was that if you were to look at the two reactions from an energy perspective, the one in blue down here needs energy. It needs energy. And so what he realized was when he heated up N2O4, it was causing it to break. And at higher temperature, the mixture darkened. What he realized was happening was he was having his jar. Yeah, having his jar, which was sealed because equilibriums have to be closed systems. Yeah, he filled it with his pale brown gas, yeah, and he added heat. And he added heat to it. And what's happening is he is driving the endothermic process. He's providing more energy for bonds to break. So the reaction gets pushed. So what happens is when he adds heat, more of the N2O4 molecules break apart to make the brown NO2. So he realized that he was favoring it. There was another consequence that he also noticed. And that is when he heated up the container, what he realized was the container didn't heat up as he expected it to. What actually happens is, similar to when you boil a kettle, when you boil a kettle, the temperature stops rising at 100. He actually plotted the temperature of the container versus the heat, by the way. And what he realized was that it wasn't actually uniform. It did this. The temperature did this. It's a rather interesting graph, I believe. The temperature rose a little, and then all of a sudden, you'd see it start to increase more rapidly until it then started to level off. Now, what's happening was, at the beginning, there were lots of molecules to break up, and it's absorbing the heat. And then when it gets to this stage, nearly all the N2O4 has broken up, and the temperature now starts to rise. And then at the end, the temperature, actually, is that correct? Yeah, and at that point, he then stopped heating it, didn't want to go any further. He was just looking for this. Actually, I don't want that tail end of it, not really much point. So what he realized was that the equilibrium was doing exactly the opposite of what he was trying to do. Now, that concept will come back later. But what I want to now do is we're focusing on temperature, and my second learning objective. So explain using particle theory. This is what we've been talking about. So we have looked at temperature and how the temperature is causing more bonds to break. So from a particle perspective, we're feeding the endothermic process, the breaking of bonds process. So the equilibrium is moving in a particular direction that favors the breaking of that bond. Now we need to use KOFS. So I've taught you kick-ass for rates. Now, by the way, kick-ass, as a pirate. There's also KOFSy. But now I'm going to teach you KOFS. So KOFS is a method, by the way. My laptop is really not doing very well today at all. This keyboard's now appeared, and I can't get rid of it. So, okay, I just want to show you what this is. So what we need to do now is go into a general perspective. General equation. So we can look at this from a general perspective. Let's go for A plus B goes to C. Now, C, of course, by the way, I could have actually just gone A, B if I wanted. Could have done that. It's actually better chemistry, really, but it's fine. So what we can realize is if this reaction is an equilibrium, we can now identify the exothermic and endothermic process. So first thing is, which one is making bonds? The forward direction is making bonds, mexo. Making is exothermic. That one there is the exo reaction. Yeah, this is because it is making a bond. A and B are binding together. The next thing we can do is, therefore, if that one's the exo, then this one must be the endo. Okay. So what we're now going to do is we're now going to decrease the temperature. We're going to put this into a question scenario. Question. We decrease temperature. We decrease temp. What happens to yield of AB? Right. So what we need to do is we need to be able to deliver this answer. This is 4 marks. It's actually 5. 5 marks in this case. Okay, so what we have to do is we have to use this to, the process we run is called KOFS. Knowledge, oppose, favor, shift. And then I often call it KOFSy because yield at the end. I don't really like KOFSy. Some people like it. I don't. I prefer KOFS. At least cough on an equilibrium. So the first thing is the knowledge. Well, we figured that bit out already. So we decrease temperature. What happens to the yield of AB? So the forward reaction is exothermic. So this K is, of course, knowledge. And this knowledge will come out of the equation. I'll put not out, but from equation. From equation. That's going to repeat over and over, by the way, if we move through the different conditions. But the knowledge is from the equation. And we've now taken from the equation that the forward reaction is exothermic. And we're going to state that. Forward reaction is exothermic. Okay, next. The next letter is oppose. Now, this one will become, you will understand it better when we then move into a different scenario. Instead of temperature, we'll look at it from a pressure perspective or a concentration. But oppose. Now, here's the thing. Equilibriums, a system, sorry, hang on, I don't need to. We decreased temperature. We decreased temperature. Now, if we decrease it, the equilibrium is going to do the exact opposite. Now, the reason, by the way, this observation was one of the key things that he observed, was the fact that when he pushed a change onto it, the change would often be, well, not often, would always be opposed. So in this case, we decrease temperature. So the equilibrium will increase temperature. You literally have to say what you did and that the equilibrium is going to do the exact opposite. But you have to actually put it in words. You have to, if I've raised the pressure, an equilibrium would reduce pressure. If I increase concentration, an equilibrium would reduce concentration. They do the exact opposite of what we do. So if it's going to do that, if it's going to increase the temperature, what is it going to favor? So which reaction is going to make the reaction hot? And the answer is, of course, exo. Exo, 3 letters, just like the word hot. So the exo reaction, so this is going to favor the exothermic reaction. So favor exothermic reaction. In this case, the reaction that makes bonds in this case. Yeah, favor exothermic reaction. Now, if it favors the exothermic reaction, and I'm going to favor it now. There's me favoring it. Yeah, bigger arrow. Yeah, I've favored it. What that means is we're going to shift from left to right. The last one is shift. And this is left to right. And what's going to happen, I don't know why I capitalized that, left to right, what's going to happen to the yield of AB? The answer is it's going to increase. Yield of AB increases. Now, I know this is tricky. Yeah, the method's good and it works really well. And once you get used to it, it becomes easier. Yeah, if you want to, now, I don't often like to try and explain this from a kinetics perspective. We can, of course, we can do that, you know, if we cool it. If we look at this, now you can't use this in your explanation. Yeah, if we cool this reaction, what's going to happen is we are going to stop supplying the heat needed here for this endothermic process. We need, this says, I need energy to break this bond. Yeah, well, if we stop feeding it, what's going to happen is it's going to stop being broken. And I decrease the temperature, it will favor. Oh, okay, I've got to look at it from an AB perspective. Let's look at this one from this perspective. Yeah, we know that this is, we can actually color code this. We can go colorless. I don't like the fact that it's not actually covered. We've got a colorless gas, and we've got a brown gas. On that side, 2 of them. Yeah, 2 of them. Colorless gas and brown gas. This is the colorless one. Colorless and brown. If we look at the temperature on this particular scenario, if we decrease the temperature, we are going to stop this bond here being broken. We're not going to be supplying the energy to do that. What that means is it's going to keep the colorless gas. So what will happen is the reaction that's turning into it is going to be favored. And what that means is if you slow down the cold reaction, and the backward reaction, of course, which is always running, will dominate, the temperature is going to increase. It's going to do the exact opposite of what I'm doing. Now, I know that this is complicated, and I know I've not done a particularly good job of this today. I really haven't. I'm going to do, let's do another one. I'm tempted to do one in an actual setting. If we do, let's do something like, but something that's observable. Chlorine gas is usually quite a good one to talk about, making and breaking bonds. If you take yellow chlorine gas in a pair, chlorine gas is a yellow gas. Yellow or green, I prefer green to be fair, it's pale green. Pale green gas. And you were to heat it up into extreme levels, by the way. If you heat it up, I don't like that. Don't like it at all. I think I've pale green gas. I'm going to heat this. I'm going to add heat. And what happens is it breaks apart into colorless atoms. Yeah, the chlorine gas molecule, and all that's happening is we're breaking a bond. Yeah, we started off with Cl2. We add lots of heat and it will break apart. Now, the great thing is, because chlorine wants to be in a pair, yeah, this will actually form an equilibrium. So what will happen is some of the atoms will turn back into chlorine. And you have the same kind of observation, this green gas to a colorless gas. So what happens is, we can say, once again, we can identify who's making and breaking bonds. So this one here, this one is breaking. Mexo-bendo. So that's the endo reaction, the cold reaction. Yeah, cold 4 letters, endo 4 letters. And then we've got the other one, which is making. Yeah, this one's making a bond. Yeah, the two atoms are coming back together and we're reforming this bond here. Yeah, so that's going to be mexo. Yeah, that's the exothermic reaction. So if I try and raise the temperature, if we raise the temp, we raise temp, ... What's going to happen? Let's just look at it from a chlorine perspective. Is it going to become green, or is it going to become colorless? Let's do, we raise the temperature, green or colorless? Question mark. Okay, so we run KOFS. As soon as we see a change in conditions, we're running KOFS. You can do KOFS if you like. So knowledge, the forward reaction is endo. Forward reaction. I'd like you to pause the video and have a go at this. Yeah, forward reaction is endothermic. It comes from the equation, step 1. Next one, oppose. We just literally write down what we did. We raised the temperature. We raised temperature. We raised temp. Equilibrium will lower temp. Right, how equal will lower temp? How will it lower the temperature? What reaction is the cold reaction? Lower means get cold. It's going to favor the breaking. It's going to favor the forward reaction. Favor forward reaction, the cold one. Forward reaction. You realize I'm translating this all the way through. Yeah, the forward reaction is endothermic, cold. Yeah, we raise the temperature. Equilibrium will lower the temperature by favoring cold, yeah, the endothermic reaction. Favor forward reaction being endo. Yeah, we can actually, let's put that back. Let's just say favor endo, it's better. Favor endothermic, favor the cold reaction. Right, shift. Right, it's going to favor the cold reaction and therefore become more colorless. Shift left to right. Left to right. It will become colorless. Yield more chlorine atoms. More chlorine atoms. It will become colorless. Turn colorless. And this is what Le Chatelier discovered. He spent his entire life putting this into practice and doing loads and loads of reactions and proving that this was the case. And he actually wrote down some lovely things in his journal. The opposition to his changes, he actually wrote down in rather poetic French. It is as if the equilibrium were alive. It's rather nice. Anyway, I'm going to leave today's lesson there. We've talked about, and we've talked about nitrogen dioxide, which is important. We've talked about the particle theory to do with making and breaking bonds, and we've had our first go at using KOFS to explain shift. Next lesson, it'll actually become, every time we move to the next one, this is temperature. So I should have put Le Chatelier's principle and temperature. But the next one we're going to do is going to be pressure or concentration. I don't know which one. I'll probably do concentration. Because it'll help continue to reinforce these this rather odd behavior that we notice from equilibriums. Just before you go, just the last nota bene. Le Chatelier's principle. A system at equilibrium, darn it, a system at equilibrium will oppose any changes in conditions placed upon it. It is as if it is alive. That's what he wrote down. And that's what he's most famous for now in chemistry. He's actually done loads of things, but he is very famous for that. Right. Well, that was a terrible, terrible lesson. I do apologize, guys. It was an absolute mess. Crashing computers all over the place. It was an absolute mess, really was. Let's see if I can turn my stupid camera back on. I know that I've also gone into lunchtime by 2 minutes. See if I can turn my camera back on. It's never crashed when I've turned it back on. There we go. Go back to StreamYard. Start camera. Start cam. It's going to go to the rear one, isn't it? Of course it is. It's really been just a really bad lesson. There we go. Let's go to that one there. Right, guys. I hope you found it useful. As I said, every time next lesson we will reinforce the use of KOFS to do all of the explanations. And the more you use it, the more you practice using it, the easier it becomes. It stops you guys. It'll stop you from waffling. You know, you don't when you get given a 4-mark question, you know, explain this change or explain this in chemistry. You guys often waffle. And KOFS, kick-ass for rates, for kinetics, and KOFS for equilibria is a really useful tool, but you do have to practice using it. It is really important. If you have any questions, please send me an email. I'm happy to respond. I hope you guys have a nice day. See you later, guys.